Here we have another example of an argument that uses quantified statements and that we can translate into a general logical form. We're going to do this very similarly to what we did earlier with universal modus ponens. So as we did in the previous lecture, I started by rewriting the quantified statement in the universal conditional format, right? For all something followed by a conditional statement. Now, referring back to this example, P of X would be, well, I went a little too far there. P of X would be X is even, and Q of X would be X is divisible by 2. Now, in the second line, again, we need to reference a specific value from the domain, and if we call that A, then I can rewrite this as not Q of A for that particular A, or A does not make A does not make Q true. Right? Then our conclusion is not P of A. In other words, A also does not make P true. Now, I want to make the same kind of comparison here as we did in the previous lecture. So on the left, I've got our new argument form from the previous slide, and on the right, I've got the form of the Modus Tollens argument. Right now, like we saw previously with the Modus Ponens versus universal Modus Ponens comparison, there are some strong similarities here. Right, both forms start with a conditional statement, and then the negation of the consequent, and they conclude with the negation of the antecedent. Right, so this is where we get the name of our new form here, and it's up in the title of the slide. This is what we call universal Modus Tollens. So I've got an example of an argument here that fits this universal Modus Tollens form. So you can pause for a minute, right, and think about what the conclusion should be based on that form. Now, referring back to our formal version of the statement, P of X would be a triangle is a right triangle, and Q of X would be the length of the sides satisfy this equation, the equation from the Pythagorean theorem. Now, the second premise here gives the dimensions of a specific triangle, which you can see again illustrated in the diagram to the right here. Now, given these dimensions, right, you can quickly confirm that they don't satisfy the equation in Q. So this part of the statement would be not Q for the specific triangle, right? And the notation here is a little bit inconvenient, right? I used A for a side length, and here we used A in our definition of universal Modus Tollens, which is kind of why I put it in here. It's a bit of a poor choice since A has already been used. We could say instead, what other letter? Let's just pick the next letter. Let's say Q of D for a particular D, and the particular D here is this triangle, right? You need to be aware of this, and this is going to become something you really need to be aware of later on when we start talking about proofs. You really don't want to reuse a variable, right? Once you've chosen a variable and you've assigned it to represent a certain thing, a certain number, a certain object, a side length in this case, you don't want to go back and try to use it for something else after the fact. Okay, so what's our conclusion here? Where our universal Modus Ponens form tells us this should make the conclusion not P of D, right, using our new variable there. In other words, again, going back to the English language here for P, we would conclude that the triangle is not a right triangle. Right, that would be our conclusion based on this universal modus tollens logical form. All right, so we've seen a couple of examples of logical forms here using universal conditional statements. What we're going to do in the next series of lectures, we're going to wrap up our discussion of predicate logic by looking at how we can validate arguments that use these statements that are based on predicates.